Hello everyone, welcome back to our low temperature thermochronology online lectures. We are studying Chapter 5, Fission Track Thermochronology, Theory Background. In the last two sections, we have been talking about fission track formation and how to calculate fission track age. In this section, we'll be learning track length analysis. The reduction of fission track age arises because the radiation damage constituting each fission track is progressively repaired at a rate which increases with temperature. This repair is manifested as a decrease in the length of individual tracks. The proportion of tracks intersecting the polished surface of an apatite grain depends on the track length, and therefore, as track length is progressively reduced, so is the fission track age. For fission track length measurement, the convention is to measure horizontal confined fission tracks. Confined track must be completely preserved in the crystal and entirely below the surface, and should be orientated parallel to the z-axis, so that their length yields the most direct and reproducible representation of the true track length. Confined tracks can be divided into two major types. One, track-in-track, or TINT for short, and two, track-in-cleavage, TINCLE for short. As is shown in the top right figure, the two confined tracks categories share a common track origin in that etchant reaches a certain confined track through a defect, for example, a crack, cleavage, surface intersecting the track, or inclusion. Confined fission tracks have a distinctive appearance in the reflected light, which is more or less in focus along the total length, and are distinguished from oblique tracks. As well as measuring the length, it is becoming more common to measure the angle of the track with respect to some reference orientation. This is because both the etching and the track shortening or annealing processes can be related to the crystallographic axis. In apatite, for example, annealing is relatively slow, but etching relatively fast for tracks parallel to the z-axis. There are some principles to be followed for recognizing confined tracks and track length measurement. First, confined tracks must be completely preserved within the crystal, and confined tracks must be parallel to the crystal surface. Besides, crystal must be orientated with its z-axis parallel to the surface. Normally, 100 or even more tracks should be measured per sample. We also need to know mean track length and standard deviation of track length distribution. Californian irradiation induces more holes in the crystal, increasing the chance of etching more confined tracks. Here are two crystals. One is Californian irradiated, and the other is not. We can see that there are some more confined tracks within the Californian irradiated crystal. The photo on the right shows a Californian irradiated apatite containing large amounts of confined tracks. It should be noted that not every feature in an etched mount is fission track. To distinguish fission tracks from features of other origins is of critical importance. As here we have two figures. On this figure to the right, we have more tracks. On this right figure, we have more dislocations. It is quite important we can distinguish dislocations from the real tracks. The above is all for Section 3. See you next time. Thank you.